Mathematics is a subject filled with infinite possibilities and zero limitations. Behind each mathematical question and method is a brilliant mind, which brought such information to light. In the case of the Moser spindle, there were two mathematicians who successfully made known this graph. William and Leo Moser were two brothers who combined their passion for mathematics to produce the Moser spindle. Leo Moser was the eldest of the two brothers, and he was born in Vienna, Austria, in 1921. At the age of 3, Leo Moser and his family immigrated to Winnipeg, Canada. He then attended the University of Manitoba. Unfortunately, he had a heart condition, which led to serious health concerns during the course of his life. Leo Moser was very successful, as he had multiple writings of his published. He eventually became a university professor. Unfortunately, Leo Moser passed away in 1970 while in his 40s. William Moser was the younger brother of Leo Moser, and he was born in 1927 in Winnipeg, Canada. Like his brother, William Moser attended the University of Manitoba, became well known in his field, published many pieces of his work, and gained several respected titles in the mathematics field. William Moser passed away much later in Montreal, Canada, in 2009.
Prior to Leo and William Moser's death, the pair were able to establish the Moser spindle, which involved their favorite area of mathematics, graphing. The Moser spindle is a unique graph that has been vital in trying to find the chromatic number of the plane. The chromatic number of the plane is the fewest number of colors needed so that no two points that are unit distance away from each other are colored the same color. For example, in this graph here, we're using an equilateral triangle. If we color the top point red, then the bottom left point would have to be green, and the final point would have to be blue. We will see how the Moser spindle relates to this concept. The spindle can be drawn as a unit distance graph, meaning each edge that connects any given vertices has length 1. Or the spindle can be drawn as a planar graph, meaning no edges intersect. However, this graph cannot be drawn as both of these at the same time.
The Moser spindle helped in establishing that the chromatic number of the plane was at least 4 in the 1900s. We now know that the chromatic number of the plane is at least 5, but when this was discovered, it put a lower bound on the chromatic number of the plane. It was very possible that it could actually have been 5, 6, or an upper bound 7, but there was no proof. Let us construct a Moser spindle to demonstrate that the chromatic number of the plane is at least 4. We will be using the non-planar unit distance representation of the Moser spindle. Recall, it also has a planar graph representation. Before starting, note that the vertices joined by the edges cannot have the same color as they are unit distant apart from each other. So, if we make vertex 1 as yellow, 2 has to be blue, and 3 has to be green. Similarly, 4 is colored as blue and 5 as green. Now either 6 or 7 can be yellow. Let us make 6 as yellow. Now 7 cannot be yellow, blue or green. Thus we have to use another color, say red. We can conclude that it is not possible to color these vertices with less than 4 colors such that all adjacent vertices has different color. This makes for the lower bound and proves that the chromatic number of the plane must be at least 4.
The big question now is, why must we care? Well, the chromatic number of the graph is used all around us. For example, to create an exam schedule for multiple classes, we would have to ensure that no 2 exam times overlap if a student is enrolled in both classes. To do this, we'd have to find the chromatic number of the graph. In terms of the Moser spindle, we could say that each vertex represented a class, and every edge that connects 2 vertices represents a student that's enrolled in both of these classes. Then these 2 class exam times cannot be scheduled at the same time. In the end, we'd see that we would need at least 4 different time slots or 4 different colors to ensure that no exam conflicts arise for any student. In addition, the Moser spindle is important because our class focuses on the idea of coloring and the idea that complete chaos is not possible. While we know that the Moser spindle proved that the chromatic number of the plane was at least 4, a recent discovery found that the chromatic number of the plane was at least 5 with the use of Moser spindles. So why did it take so long? Well, the difference is the Moser spindle has only 7 vertices, but it took a graph of over 1,500 vertices to prove that the chromatic number of the plane was at least 5 using a lot of computations. The big questions now are, can this graph be reduced to a smaller number of vertices, and what is the real chromatic number of the plane? Could it be 6? Similar to Ramsey numbers, this once again fits into the idea that complete chaos is not possible. So, if the chromatic number of the plane was actually 6, which we don't know as of right now, and aliens invaded and told us to prove it, it could very well be possible now through the power of computation. In this sense, we can say the chromatic number of the plane is still an open question. But there is one thing we can count on for sure. We can count on computers to solve this problem one day, as they can prove many things we can't do by hand. Together, Leo and William Moser made a tremendous impact on the field of mathematics. They created the Moser spindle, being a few of the first mathematicians to shed light on the chromatic number of the plane. To end, we have a quote spoken by William Moser in 2003 when he earned the Distinguished Service Award. It states, "Be generous and patient as teachers. Be active in projects which benefit the mathematical community, and above all, have as long and as happy a mathematical life as I have had and am still having."